Hello everybody, welcome to another one of our class videos. I wanted to put together an additional video showing an example about a related rate problem involving similar triangles, since those are somewhat different than the ones that we've done up to this point. Obviously our learning goal would be that you will be able to solve related rates problems involving similar triangles. So let's look at this example to see what makes it different. So here's our example. Dawson, who is 5 feet tall, is walking toward a 20-foot tall light post at night at a rate of 3 feet per second. How fast is the length of his shadow changing at the moment he is 12 feet from the light post? Okay, so as we examine this example, I'll be again applying the principles of radar that we've shown in previous videos, where we will read the problem, ask what it's asking for, decode it, apply our knowledge, and ask if the answer is reasonable. So, here we go. We've already read the problem, so let's see, what is it asking for? It asked, how fast is the length of his shadow changing? Okay, so how fast would mean that the word fast there implies a rate, and when I'm thinking rate, I'm thinking derivative. Okay, so it is asking me to find, I'm going to use the letter L for the length of his shadow. I would otherwise use S, but my S's look like 5s, and I don't want to get you all confused. So L it is. So we're finding the derivative of the length of the shadow with respect to time. At the moment, he is 12 feet from the light post. So when something equals 12, well, I guess I need to assign a variable to that. See, 12 feet from the light post, that would be his distance from the light post. So let's go with D. I'm going to call that D for distance. Okay, so we have what it's asking us to find. Great, let's go in through and decode the rest of the problem to make sense of it. The first piece of information they tell us is that Dawson is 5 feet tall. I should probably be drawing a picture at this point, so let me draw him. Here's Dawson, he's 5 feet tall. Great. Alright, then he is walking toward. Toward is going to be an important word here. The direction of his travel is going to tell us whether certain derivatives are positive or negative. So we'll need to make sure we pay attention to that later. He is walking toward a 20-foot tall light post. So let me draw that. There it is. Nice light post, don't you think? Okay. So now that I have those pieces of information in there, I can start drawing in some of the variables that I identified before. The distance between Dawson and the light post is given by the letter D. Then the light creates a shadow. The way it creates a shadow is the light rays from the lamppost hit Dawson's head, and then it creates a shadow on the ground, which has a length of L, which we already decided on before. Okay, so now we have the picture going. Let's continue reading the problem. He's walking at night, hence the shadow, at a rate of 3 feet per second. Okay, so that's a rate. Rate, I'm thinking derivative again. So I'm given that d something dt is 3 feet per second. What is the something? That would be his distance from the light post is changing at a rate of 3 feet per second. In particular here, he is walking toward the light post, so that distance d is decreasing. Hence, that dt, oh great, I just did make it more confusing with the letter D, didn't I? Oh well, okay, so dt is negative 3 feet per second because d is decreasing by 3 feet per second. Okay, so I have that information. We also know from doing previous problems that we want to have a snapshot picture as well. So let's draw that snapshot picture. I'm going to do a copy of this picture, but I'm going to replace the variables with the values that they actually are at that snapshot that I'm interested in. Okay, in this snapshot image, the distance that Dawson is from the light post is 12 feet, so I marked that in there. Now, am I told what the length of his shadow is at that point? No. Could I figure it out? Yes. Do I know that I need it? Well, I might not need it. So let's just leave it blank in case maybe I don't need to calculate that at all. Why calculate something if I don't have to, right? Okay, so there I have my picture with the variables on the left and my snapshot picture with only constants on the right. So now I need an equation. We're now applying our knowledge to the related rate situation here. I need an equation that relates the two variables, D and L. What do y'all think that might be? Got any ideas? Pause the video for a sec. Got something? Some of y'all might be thinking the Pythagorean theorem, and there are right triangles in the picture. However, we know nothing about the hypotenuse, so that actually won't work if you were thinking that. But good try though. In this case, because the triangles are similar, we'll need a proportion. To facilitate that, I'm going to split the triangles into two separate triangles. You see the larger right triangle and the smaller right triangle. Y'all remember this from geometry? If you had me for geometry and you watched my geometry videos, you would have seen this technique. But in case you hadn't, we're taking the two triangles in that one situation and splitting them up. So I have 20 feet for the light post, 5 feet for Dawson, and L for the length of his shadow. So the small triangle is this one right here. Okay, then what goes there? What do you think? Is it D? Well, no, because D only covers part of that side of the triangle, not the whole thing. What is it? It's the length of this entire side of the triangle is D plus L. Okay, the sum of both of those makes that entire triangle. So I'm going to put D plus L there. Okay, so now I have my two triangles split up separately. Now it'd be easy for me to set up a proportion. Here we go, just recreate that picture. Now, so a proportion looks like a fraction equals a fraction. A ratio equals a ratio. Either way. Okay? I'm going to set up this side, the one for the smaller triangle, as 5 over L. So that is the vertical distance over the horizontal distance. What would go on the left side? That would be 20 over D plus L. You just follow the same pattern. You could have easily done the reverse as well. As long as you match up the sides appropriately, then your proportion will work. Okay, so I have an equation relating D and L. It's time to take the derivative of both sides, right? Oh, yuck. That doing the derivative at this point would be, well, I'd have to use either the quotient rule on both sides or the chain rule, and with rewriting it as a negative power, and like, oh gosh, okay, I'm not doing that. Okay, how about we can manipulate this equation a little bit first to make it a little nicer. So maybe we could cross multiply. That's what we would usually do with a proportion. I don't have to do the derivative right away. I can manipulate the equation all I want until I get it to look the way that's convenient for me. Okay, so let's cross multiply. What would you get? If you cross multiply the D plus L times the 5, you would get 5 times quantity D plus L. Remember that you have to put the parentheses there so that you can distribute. Okay, the 5 has to get multiplied by that entire quantity. On the right side, you would have 20 times L, or 20L. Alright, well I could take the derivative here, right? I can manipulate this more, and why not? I'll just go ahead and distribute. Why not? I mean, no big deal. Oh, and look, I can conveniently subtract 5L from both sides. I'm going to just manipulate this till the cows come home. Alright, so now that, well, I could do the derivative here, but, well, okay, I can manipulate it some more. Let's divide both sides by 5. Okay, now that looks pretty simple, doesn't it? So I decided to just change this equation around and keep playing with it until I get to something that looks pretty simple. D is just simply 3 times the length of the shadow. That's pretty cool. Alright, Now we're at a point where we can take the derivative of both sides with respect to time. What would go on the left side? Well, derivative of d with respect to time would just be derivative of d with respect to time, which is d dt. Okay, what about on the right-hand side? What would we have? That would be 3 dl dt. Okay, the 3 being a constant multiple just comes along for the ride. Okay, so now I have an equation relating the derivatives. I'm now at the point where I can plug in. Great. Going back to the information which we had before, okay, I have what I'm trying to find, which is dl dt, and what I'm given, which is that d dt is negative 3 feet per second. Notice here that the d equals 12 didn't actually matter at all. Sometimes it will matter, a lot of times it will, but in this case it didn't. That d doesn't even appear in my equation for me to plug it into. Alright, so let me just plug in the d dt that they gave me, negative 3 feet per second. Alright, and then I need to solve for dl dt. Well, that's simple. I can just divide 3 on both sides. I get negative 1 feet per second. Is that answer reasonable? Well, I do consider that dl dt is less than 0. It's negative, which makes sense. His shadow should be getting shorter the closer he walks to the light post. That checks out. And also the units of feet per second is reasonable. So I think it sounds pretty good to me. At this point, it would bear to show a shortcut that we could have used on this problem, only because of a certain way it was set up. It wouldn't be possible to use on every single similar triangles problem. Here again are our triangles, and I want you to observe something. Okay, see how the scale factor from the small triangle to the large one is 4? In other words, the larger right triangle is 4 times the size of the small one. That would mean that the base of the triangle would have to be 4 times L. Okay, that's, again, 4 times the size of the smaller triangle. If I know that that whole side is 4L, and D plus L gives me 4L, well, how many L's was D? Well, D had to be 3 L's. Oh, that's the equation we just got. Take the derivative of both sides, bam, we get right here right immediately. That shortcut worked only because the scale factor was easily identifiable from the information that we had. If we couldn't tell, like for example we had a variable on one of the heights of the triangle, then it wouldn't be easy to tell what the scale factor was, and hence setting up the equations wouldn't work that way. However, we could still set up a proportion just like we had. Okay, well, I think that's the end. I will see you guys in class.